thanks a lot for inviting me to this event, and I'm very pleased to be here and talk about this topic that I have been working with for now like 5 years. So I'm strategic product manager for time critical communication with Andersson. So today I will give an introduction to a high level view on the time critical communication, and also go into one important topic related to this that is called rate adaptation. So let us dig into the presentation here. I mean, as 5G is now getting very well established, we are now looking into for the next big things in around 5G, and we see that many of the emerging use cases are what we call time critical. So that means that they demand a new type of connectivity that can deliver consistent low latency and also reliability. So this is a fundamental difference from like mobile broadband connectivity in the networks today, that instead of prioritizing the data throughput with best effort latency compared to then time critical communication. So we believe that this will drive next wave of innovation for 5G consumers. So today we have addressed, as written here further down to the right, 6 major causes of latency in the networks today, and we are working then towards reducing and eliminating those in all these areas. Two areas that I would like to mention today are in more detail is around congestion and radio environments. And these are examples of causes leading then to reduced quality of service and can result in bad quality of service experience for the users. And this can then, having a network node or connection to carry more data than it can actually handle. So a few use cases, then a typical use cases that would benefit them from some congestion control are this cloud mobile gaming, for example. We have different extended reality type of use cases such as cloud AR and cloud VR. We have also different remote control type of use cases, like you see the drone remote control and also the remote driving. And the common denominator for all these is that we have like some media content that can be rate adapted in either both directions, in downlink and uplink, or either in one direction, for example, for the remote control, for example. So here to set the scene then for the rate adaptation technology in cellular networks, I would like to start with a brief reminder of the characteristics then of radio communication. So if you look to the left of this slide, we have radio coverage in a cellular network is then provided by like different investments and densification, making sure that the radio signal is strong enough at all locations in your desired area. So without sufficient signal strength, then your communication cannot take place, basically. And the traffic load situation as well in the network where you have your devices is essential, as seen also to the upper right picture here. So if there's a lot of competing traffic here, for example, shown during the daytime in a traffic load graph here, the bandwidth for a particular user may become limited, and queues can easily be built up, leading to network latency. So to address this, sensitive or time critical traffic needs to be prioritized for having better user experience. But of course, not all traffic can be prioritized. So only a part of the traffic can have this higher priority. Also to the lower right, I also want to highlight that radio links also vary over time, as you can see in this example here. So when the application needs more bandwidth, then the radio channel can deliver, which can be seen when the purple graph is above the yellow graph, so to say. The variations here are triggered as the user moves around, sometimes around a corner of a building. And this can of course then lead to attenuation of signal fading. So in these scenarios with high traffic load and or variations in the radio environment, we think that rate adaptation is key to be able to support the intended use case that I showed in the previous slide, and also to improve user experience for maybe the AR, XR type of use case and the cloud gaming. So just to list the different options here. So there are 3 approaches that I will just mention briefly here in this slide. So we have the baseline here, basically over the top. There is no network support. It's based on end-to-end protocol feedback, and the congestion control is then handled within the end nodes. But there is some limitations to this. These endpoint latency estimators here, I mean here depicted on the receiver and the sender side, they cannot identify the source of the latency variations. And today they're using different techniques such as like filtering or averaging of the jitter to avoid an overreaction of the rate adaptation filter. And due to this technology, that means then that there will be a later reaction on the rate adaptation compared to other techniques that I will show here later in this slide. So if we go to the next one, so this is then the low L4S, what's called low latency, low loss scalable throughput. So then we believe that the G0B is a good observation point for reflecting both the application data rate as well as the channel quality. And then this G0B congestion marking can occur then even before it's visible in the delay jitter noise on the application side. And as previously said, I mean in the previous slide here, I mean largest contributors to these harmful latency spikes is then the combination of the radio channel and changes in application rate. So some characteristics of the L4S then is that I mean it's decoupled, transparent, and it's independence between the app and the networks. It is end-to-end. It's also common to multiple access technologies, so it's not only for 3GPP, but can also work with other type of radio equipment, switches, and even Wi-Fi nodes and so forth. So it's not only applicable to the radio interface, but also to other potential bottlenecks in the links. And it's also specified here in this IETF, which is then this Internet Engineering Task Force. So, and it's using then what we call in-band, and it scales then with the number of users here. The third option here I would like to address as well is the API based. So at the moment we believe that it will have similar performance in the rate adaptation. But there's some different there are some different characteristics since it's a different way to handle. So here we have like a tight coupling then between the application and the network. So I mean both the RAN and of course the application needs to support the common API here. So there needs to be like an agreement between the app provider and multiple networks, and require standardized and aligned APIs for all mobile networks here. There also needs to be some application authorization going through these interfaces, and it's also now limited on the 3GPP networks. And also depending on the solution here, there will be like also predefined rate levels, and they could be both less or more fine-grained, and using different operational modes here. could be a risk for like under utilization, for example. So these are the different options that are on the table. So in the following slides here in this presentation, I will have an extra look on the L4S type of rate adaptation. So we'll go into a little bit more detail on that. So this is then a high-level view or an overview of then L4S support in 5G RAN. So it's like then a method for like conveying fast congestion information to the application. The technology here was originally defined for wired networks and is specified in this internet standardization organization that I mentioned here in the previous one. So compared to then, I mean, conventional transport protocol, L4S then uses far denser congestion events to achieve the purpose here, which then, I mean, the purpose then is to, of course, have low delay jitter and having very low queue delays. And of course, still maintaining a high link utilization. So let's start here, I mean, with just the overall architecture of this communication structure here. So you can, if we start with the upper left picture here, you can see the downlink and uplink data flows that can be followed and through the network here, through the orange and red signal flows. So the L4S capable queue management will already when these delays are quite low, will immediately start to mark the L4S capable packet. And so of course this is depending on configuration, and it can be configured at different levels of queue delays that you want to achieve. So the marking is done in the forward solid line direction of the end-to-end flow, and then collected by the client side and sent in a feedback protocol shown then here in this dashed line of the top left here to the server, and this then gives quite prompt reaction to signs of congestion, allowing then the application to implement and scalable rate adaptation. Then proportion, of course, to the number of marked packets it will receive. So if you look at a certain time window, you can collect the number of marked packets, and based on that information, the application can take action to rate that accordingly. And of course, here the protocol, I mean, the procedure is same for both downlink and uplink. And it's also, as mentioned before, it's regardless if the server is on the network or on the UE side, so to say. Some more details also further down here in the IP header. I mean, it's already prepared for congestion marking, right? So here you can see the 2 bits in the IP header devoted for this. These bits allow then the application to indicate if it's an L4S capable data flow and enable then any network node to indicate this congestion. So yeah, so there are clear benefits. I mean, compared to ordinary transport nodes, the capacity of the RAN transport media may suffer from these rapid changes that I talked about in variations of radio. And of course, addition to this current queue, the channel quality metrics also contribute to a more proactive reaction than to this congestion. So if you can take a look maybe on the bottom left here, and maybe you can have a look inside the GNB here. There is a bit functionality, and it can be divided into these different function blocks here. Where as there is encryption,
please keep muted.
Sorry, can you keep muted there?
岳喜亮, please keep muted. Thank you. Sorry, please go ahead.
Yeah, so I was just explaining here the different nodes here. So we have here the different function blocks. A congestion detection function, a marking probability function. We set it the activity to mark a portion of the packets according then to the calculated marking probability here, so to say. Yes, I think, and then we have the L4S essentials here up in the blue box to the right. So I think I covered this when I was speaking about the slides. So let's have just have a look here on some of the results. So we have, been doing quite a lot of measurements conducted in both lab and live environment, and we see that this method and facilitate and this trade between throughput and latency. And you can see here with the unassisted rate adaptation here in the picture furthest up here to the left, you can see the bit rate in the orange curve, and you can see that the Q delay here in the with the blue curve here. So you can see that it's varying. The Q delay is varying a lot here in this scenario where we're not having any rate adaptation. And if we take a look then with the network assisted rate adaptation scenario here to the right, we can see then if we look at the Q delay, that is quite flat here, the blue line that you can see here. So we are keeping the latency low. Of course, it comes to a cost, since the bit rate here, you can see the average bit rate is a bit lower, but as we are focusing on the latency of the packets here, we consider that as the more important in this case. We actually achieve a goal here with this scenario. And on top of this, you can see also the green curve here, and that is actually the CE marking, how much are we tagging those packets where we have we are building up congestion. And you can see that there is a few spikes here of marking, and that we are acting accordingly, and the actual bit rate is going slightly down after this marking here in this case. So we can see improvements in this example of downlink latency, still maintaining the required throughput and so forth. On the and then this is just the Q delay. It's another just view. It's like a CDF, another way of expressing then this Q delay here. You can see that that it's the Q delay is more it's with less. It's more stable with the L4S assisted the algorithm compared to without. And then just to finalize, here is like this boat game that we have put together, like a short demo that compares the experience then of this boat rate application to run over cellular network with and without L4S, running side by side. And of course, to test here, we have also added impairments such as slow fading, variable signal attenuation, randomized background traffic, and this is similar for both for the comparison here. So the impairments here are exactly the same for both the video streams with and without rate adaptation here. There are some links here to if you want to look in more details on this part. And here you can also say in the curve. Let's just wrap up this. So we have here the white one is the round trip time latency, and we have the bit rate here as well, similar to the previous slide here where we're in the graphs. And here to the right we are adding then the L4S, and you can, if you look carefully, you can see the red L4S marking here, and you can see that the latency is of course kept more stable here in the right. Again, with some cost also to the throughput, of course. Now I realized I was running a little bit over time, so sorry for that. But this was the last slide I was having for this presentation.